All right, welcome to today's lecture. Today we're going to be talking about bitwise operators in C and then also focusing on the Endianness, so little endian versus big endian, which is how data is stored in the computer. With the bitwise operations, and this is really just a review, the only thing that's different is that we're looking at these as the C operators instead of the instructions in assembly, which we've already covered. So XOR and the shift operations, shift arithmetic right and left, as well as just shift left and shift right, logical and logical not. They're the same thing. They're just, these are the operators that we can implement those inside a C. Not every language allows you to do this, and so there's going to find occasion where you do need to work at that bit and byte level, and these are going to be the only ways that you can do that using these logical operations. Here you can see, so if you ever find these characters in a program, then this is what that program's author is doing, is a bitwise operation. So a single ampersand is the logical AND, a single vertical pipe is logical OR, the caret is a logical XOR, tilde is logical NOT, and then the greater than, less than are the shift operations. I put together a simple example program, and it looks maybe a little bit like there's a little bit going on here, but there really isn't. What this program does is a simple XOR, and that's actually something that is used oftentimes to not necessarily obfuscate data. Well, I guess it is, to obfuscate it just a little bit. It's not full of encryption, and it's not a very robust obfuscation routine, but it does allow us to do a little bit of obfuscation. Malware sometimes will do that, in that they'll embed inside of a Windows executable, in the resource section, they'll embed another executable. And so that main program's job, it's called a dropper, what it'll do is it'll extract that code and then it'll execute it. Well, if it's XORed, what they're hoping to do is to bypass antivirus and anti-malware scanners. And so relatively simple, but sometimes can be fairly effective. The code itself I've uploaded to our class folder, so you can take a look at that if you'd like. What it's doing is I'm just declaring a couple of char buffers. So we've got about 500 bytes for input and 500 bytes for output. I'm not guaranteeing this is not susceptible to some sort of a buffer overflow or anything. What you're going to do then is you're going to enter in a value. So just type in some sort of a string value, enter in a key. In this case, I'm just going to type in something numeric. And then what this function will do is you can see that as long as it's not 0, so as long as the characters that we're encoding is not the null byte and the input that we're looking at is not the key, then we're taking that value and we're XORing it with the key that was put in. So we're taking that original char array, that string that the user types in, and we're XORing it using the XOR operator with the key itself. For those that are null, or it is the key, then we don't do any XOR. The nice thing about XOR, I guess in a way, is that it's relatively simple to go back to the original value. And so what you can see here is essentially that same loop going through and XORing those values with the key, and we get the original result. So let's see, I've got this set up here. Make the text a little bit bigger. I've already compiled the program. You can run it, enter a value. So we'll just type in something simple like CSC 314, and then our XOR key 9. So there's the XOR value and an attempt to be printable characters, and then that's the value when it's XORed against the key again, which is the original text. So it's really inexpensive to go back and forth between a value that's been XORed. And if you get into the malware analysis and the reverse engineering, you'll likely talk more about that. Okay, so that's just an example of using that in practice. Here are some more of the bit operations, and I'll just leave this chart here. If you'd like a little extra practice, you can go through and try to figure out the answers, and if you're unsure, send me an email or something, and I'll be more than happy to send you or walk you through, make sure you got the results that are correct. Alright, so on to Endianness. So we have little versus big, and why we care about this is because the Endianness determines how the data is actually stored in memory, on disk in the system. And so big endian will store the most significant byte first, which is our acronym here, MSB, most significant byte, and little endian will store the least significant byte first. And so we'll have an example here. We'll go through and code in just a moment. This only affects multi-byte data. It doesn't affect the bits and it doesn't affect the byte. And so only when we have word or D-word or quad word or something larger does the Endianness matter. And we'll go through some examples here throughout this video, and hopefully that'll be clear exactly why that is. Here's an example memory diagram, and it's important to understand this conceptually in how this data is being stored in order to understand the difference between the Endianness, big and little. If this is the way that memory is being allocated, right, we have lower addresses to higher addresses. And so you can see with this byte offset 04812, what this is showing us is that as we're allocating memory, as we're getting memory assigned to our program and the data that we want to use in it, we're going to start with lower addresses and move our way to higher addresses. What this chart is also depicting is that memory is typically stored. We store at a minimum 1 byte, and then we oftentimes, due to data alignment issues and performance issues with accessing memory, we oftentimes will store those 4 bytes wide. And so you can see here, byte 0, 1, 2, and 3, this is 4 bytes. And so we're storing data. As we're getting it assigned, as we're requesting data, memory to store our data in, we're going to start with this block, and then we're going to move from byte 0 to byte 1 to byte 2 to byte 3, 4, 5, 6, 7, and so forth and so on. All the way through until we have the amount of memory that we've requested. It's this memory layout and how these addresses are assigned, starting at the lowest and then working its way up to our higher addresses. It's how this is assigned that has an impact on the little or big, because little will put the least significant bytes first, and big will put the most significant bytes first. Right? So when we go to access this data, the bytes that we read will be different depending on what's stored in these locations. Right, so here's an example, very similar to the previous, just not quite as drawn out. We have little and big, and so if we're looking at lower to higher addresses, then with big Endianness, so big, we're storing the most significant bytes first, right? So we store the most significant, so the bits that would have the biggest impact on the total value, that data, if a bit was changed, right? So if we have 00 A, B, C, D, E, F, 00 is stored first, right? If we go back to this example, byte 0 would be 00. Then we would have AB, then we would have CD, and then we finally have EF. Right? With little endian, it's the exact opposite. We would store the least significant bytes first. Right? So if this is the first address assigned to us to store data, EF would go here, then CD, then AB, and then 00. As you can see, this is multi-byte data, and it's stored in exactly the opposite order due to the endianness. Okay, here's an example from the book. So if you were just interested in looking at a program or a way to determine the endianness of a machine, you could use an example program like this. Right? If we stored the hex values 1, 2, 3, 4 in hex, and we returned the first element being 1, 2, right? Those are the most significant bytes, and if that's what's stored there, if that's the data that's returned in that position in that array, then we know it's a big endian. It's stored in big endian. Otherwise, it's a little endian. So that's just an example there if you wanted to go through, write up that program, and just kind of trace through it to make sure you understand what's going on. Again, why does it matter? Well, it matters when we store multi-byte data, a word or a D word or a quad word or something larger, because how that data is stored then, how it's laid out will depend on the endianness. Bytes, it doesn't matter, because a byte is a byte, and it doesn't matter. We'll store the data in the byte as that memory address is allocated for us or assigned to us. And again, I got an example here, diagram, a couple slides down, along with the program. And we'll go through a sample program. So it's used in, one of the more practical purposes is that it's used with network traffic. And so network traffic uses big endian. And so oftentimes what you'll see, especially in programs that do any sort of communication over a network, any sort of socket programming, TCP and UDP, is you'll see that it has to make a conversion. You have to make a conversion from little endian to big endian. And so there are two common C functions. We'll take a look at one today, host to network and network to host. And so you can see that what these functions do, really pretty straightforward. They simply swap the byte order. So they take from little endian and they prepare it to be transferred over a host or over a network. So they make it big endian because that's what the byte order that's expected on the network. So we'll take a look at an example of there. This is a sample program that creates I guess you could call it a reverse shell. Sometimes I use it for that, but all it's doing is it's connecting, or it's creating a socket connection. And so you'll find some of the calls, htons host to network, right, on the port, and some other of those functions that are changing the byte order so that it's ready for transfer over the network. And you can see even some of the comments here that I include is it helps with endianness. It doesn't help with it. It prepares little endian for big Endian. And so I don't have this code uploaded. If you're interested in that, let me know. I'd be more than happy to share that with you. Here's an example. So we'll start off with this. And this diagram hopefully looks familiar. Hopefully it looks a little bit like this original diagram that we talked about here. But what I've done is I've also added some variables. And so let's say that we allocate these three labels, these three variables with this corresponding data. So string, hello, and Bob. String's a D word, right? So we have 4 bytes, and the value is 00, AA, BB, CC. So what will happen then, these are our lower addresses, these go up to higher addresses, then we'll store the least significant bytes first, or the least significant byte first, which is CC. So that gets stored in the first address, then BB, which gets stored in the next, then AA, which is in the third, and then 00. Right? So that's now 4 bytes. This is 4 bytes wide. Okay, the next one is a D word. So that's 2 bytes. And so we store this 0F first. So this is the next address that would be available for us. Each block here represents a byte. So 0F. That's all the data, but because we said this is a word, we have 2 bytes. We also have a 00 put into this location. So those are the 2 bytes that we consume. Okay, now Bob's a little different because you can see with this string, right, we stored the least significant byte first. So we started with CC, then BB, then AA, then 00. But with Bob, because I define these as a byte, what happens is we just start assigning the data 1 byte at a time. Right? It has to be multi-byte data in order for the Endianness to be a factor. So we get the first address for B, which is B, then the next address, which is a byte for O, and then B, and then our new line characters, so hex A, and then 00 for a null termination. Right? So those are just stored in the order in which they're allocated for us because it's only 1 byte. Right? So you can see the difference between Bob as a series of bytes, which is stored right here, and string, which is a D word, which starts with the storage of the data with the least significant byte first. Alright, so just keep in mind the smallest amount of memory that we can utilize, transfer, store, read is a byte. There's a couple of other things that we can do in order to assist us with swapping of bytes if we need to do that. bswap, and that swaps the bytes of a register. So we could say something like bswap EAX, and we'll do that here in a moment. You can also exchange. So if you need to exchange maybe the upper 8 bits of AX or the lower 8 bits of AX, you could do that. And so you have a couple of options here as far as getting bytes to be swapped around. Alright, so let's take a look at an example. Alright, so we'll start first with data. Okay, so I've declared this as a D word, 00, A, B, C, D, E, F. So the first thing that we'll do is I'm going to move this into EAX, but before that I'm going to zero out EAX. And now I'm going to move into EAX, not the memory, not the address, but the actual data. So we'll use the brackets to dereference that. We'll do a dump regs, and now we'll see the output. Okay, perhaps we'll see some output. Make sure that I'm in fact connected. Okay. Alright, so I'll do that over again, move into EAX 0, and then move into EAX the data that's stored at that location. Now we'll dump regs. There we go. Okay, so you can see that I have the value 00AA or 00ABCDEF, and it looks like that is what we'd expect. We have in the register the value 00ABCDEF. Where it becomes a little more apparent that we're working with little endian is, let's say that now I want to move, so let's clear out EBX, and let's just move into AX the first 16 bits or 2 bytes of data. And let's dump the register and see what we get. Oops, sorry, that was AX, meant to do BX. Okay, try that again. Okay, so with EBX, we have CDEF, right? What happened is that we said, let's read the first 2 bytes of data, 2 bytes that's at this location. And so because it's stored EF, right, we store little endian, so least significant byte first, EFCD, what we ended up doing is we read EF and then CD. Right? We didn't read 00 AB, we read EFCD. We read from least significant byte first to most significant byte instead of most significant byte to least significant byte. So you can really see the difference there. We could obviously continue with that, and we can just use ECX, and we can move into CL data. So we'll move the first byte into CL, and if we dump that, you'll see that we're just moving EF. Those are the first bytes that we access that's stored for that data. Okay, so that's what you have to keep in mind especially when you're programming an assembly and you're dealing with the bits and bytes. Most of the time, if you wanted to reference this data, you'd move the entire thing into the register, and you wouldn't really have to worry about it. But when you start, but it definitely can be an issue that you'll run into. Let's see. We have. Let's do an extern. So we have defined 2 externs. We talked about those in the last video: network to host and host to network. And so now we can, we have into EAX the value from data. And so we can push, in order to call that, we have to push what we want to swap onto the stack. And then we can call host to network. And we need to make sure that we do a call. So host to network. All right, and now that will return in EAX the value of the data that we pushed in reverse order. So I'll do a dump regs. I'm going to comment some of these out here as we go, just to produce a little less cluster. All right, and we can see in EAX that has been swapped completely. So 00AB, CDEF. Right, it's backwards. Remember though that when we're doing a swap, we're doing it a byte at a time. Right, so 00 AB, CD, EF. Right, so it's important to note that, to understand that. Okay, so that's an example of calling the host to network. And then if you wanted to do the opposite of that, right, network to host would swap it to the other direction. All right. So if we use some of these other variables that I talked about in the memory diagram slide, what we can do is we can just move those into registers and see what happens. So let's move into ECX0 just to zero that out, and then move into ECX a value of hello, and then we'll dump the regs. Okay, so there is our data, 0F. Okay, even though we zeroed that out, we got some cruft at the top of the register there, but 0F is all we have. That's all the data that we moved into that location. Why did we get that? Well, because hello is a word. We moved it into ECX, and so we might need to do. And that wouldn't work because that's a word. And so we have a mismatch in data. And so in this case, we might want to do something like a sign extend or a zero extend. We could try that. That would be probably a little more appropriate here. Okay. Let's just do this. We'll do appropriately sized. Hello. There we go. All right, so now we can dump that register. We shouldn't have any issues there. Segmentation fault, okay. CX, all right, so there we go. And there's our 000F. Okay, you saw I was getting a segmentation fault, and the reason that was because I forgot to adjust the stack. So, and again, we'll talk about the stack here in the upcoming weeks, and we'll spend a good amount of time on that. So don't worry too much about that. But just so you know that there was a segmentation error there, segmentation fault, and that was the way to fix that. All right, so the last thing that we'll look at then is, let's say that we want to move into, let's just use EDX, we'll zero that out, and then we'll move into EDX the data that is Bob. Okay, and then we'll dump the regs 5. Okay, so here's EDX. All right, and you can see that because those are ASCII characters, we're getting their their hex equivalent. So if we really wanted to figure out, we can tell 62 is B. If we weren't sure though, we could look that up. We could go to the ASCII table and look that up. What's happening though is, again, it's different than when we store something that's larger than a byte in Little Endian. We start reading data at that location where we just do it, a byte at a time. And so we start with, and even though this is only going to give us the 4 bytes for that register, right? This is a little bit larger than that because we define this as a byte. We have 1, 2, 3, 4, 5 bytes, including the null termination. And so it starts to move that data in, but because B is assigned the first address, then O is assigned the next address, then B is assigned the third, and so forth. That's the order in which it was moved in. So 62, B, 6F, O, 62B, and then 08, which is our new line. And so we can see that that's a little bit different than what we might have expected if it were moving in one of these, one of these other examples, these multi-byte examples. Okay, so there's the example there. Just like the network to host, just so you can see an example, we can also do bswap. Okay, so we can say bswap EAX, and then we can dump breaks 6. And now you'll see that here we had it in a different byte order from our call to host to network, and now we've swapped those bytes again. So now it's back to the original value. So another example there of using the byte swap. All right, so I think that's about it. That's everything I wanted to cover. If you have any questions on this, let me know. Otherwise, we'll pick up next week with some new material. So thanks a lot, and I'll talk to you then.